Okay, so lesson 12.2 is conditional probability. Still the basic idea of probability, but conditional probability, where it's the probability of something given some condition that must occur, okay, or must be true. So by definition, conditional probability, the probability that an event B will occur given that another event A has already occurred. The notation, that's probability of B slash A is what it looks like to you guys, but it's read the probability of event B given event A. So for any two events A and B in the sample space, so in the possible answers, probability of B given event A, on top you're going to do the probability of A and B together, and then on bottom it's the probability of A. Okay? Now we're going to look at a couple examples to get us into this, and I will say on the first example I'm going to kind of show you the long way, but we can kind of then shortcut it. So first example, a student committee is being formed to decide how after-school activities will be funded. The committee members are selected at random from current club members. The frequency table shows the current club membership data. Okay, so you guys can read. You see the categories of sophomore, junior, seniors, the categories of drama, science, art, and the various totals. And our first question that we're going to work on here, what is the probability that a member of the art club selected at random is a junior? Okay. So one of the things we're going to practice is putting it into this form. I will say sometimes you'll just be given that form. If you look later in the notes, you'll see where it's just given that form. We don't have to get into that form. But we also need to have the understanding to get it into that form. And so we have to look at what is it they're asking. We want to know overall what is the probability that the student is a not just art club member, but specifically a junior art club member. And so the way this one is worded, this is what is the probability that a member of the art club selected at random is junior. So what is the probability that the student is a junior, given what has to be true? They have to be a member of the art club. So if I write this, I'm going to write it as the probability of junior slash, and then member of the art club. Okay? That's the problem we're trying to look at there. So what is the probability that the student is a junior, given they are a member of art club? Now, officially, if we look at this setup, what's that say we're going to do? On top, we're doing the probability of A and B. So that's going to be the probability that the student is a junior and in art. Where do I want to put this? And again, I think I'm going to go the long way first, and then we'll be able to figure out the shortcut. So probably the member is a junior and in art, divided by what's it supposed to be? The probability of A, which the probability of A is the probability that they are a member of art club. Okay. So, probability that the student is a junior and in art. So probability that both is true. What do you see here? Okay. 16 students are juniors and in art out of 115 in total, yes? So this is going to be 16. Should have set this up differently. Oh well. Over 115 divided by probably the student is an member of art club. Member of art club is 58 out of again the total of 115. Okay. Now, what do you notice there? They both got the 115s there, don't they? Now, officially, the long way is we're dividing fractions. The short way is if the denominators are the same, guess what they're going to do? They're going to end up canceling out. How do we, okay, let's look at the math behind it. How do we divide fractions? Some of you are seeing this and going, oh my gosh, ugly, I don't know what to do. How do we divide fractions? Keep, change, flip, yes? So if I keep, change, flip, I'm keeping 16 over 115, changing division to multiplication, and I'm flipping. So instead of dividing by 58 over 115, I'm multiplying by 115 over 158. What do those 115s do? They cross cancel, yes? And so then you're ending up with 16 over 58, which, I don't know. I know they're both even, so I know they're reduced that way. And what are they both reduced to? 8 over 29. Does that go farther? No. 8 out of 20, or 29 is prime, so I know it can't divide into anything else. Okay. Now, no one wants to divide fractions every time. No one wants to divide fractions, period. I know how we all are. Okay. Notice these denominators were the same, yes? And that is a true thing. When you're dividing two fractions and the denominators are the same like this, they're automatically going to cancel. Here's the math to prove. Okay. Now, so when we set this up, we did probability over probability, doing the official. Okay. Now, what's the shortcut that we could have just done then? Could we have eliminated the 115s from the get-go? You can. Okay. You definitely can. When we looked at this, we could have just automatically looked at, what was it? It was on top was the total number of, I'm trying to think how I wrote it in my, on top was the total number of juniors in art club, right? And on bottom was just the total art club members. Okay. If you do some comparison, I probably should have said total art club members, sorry. I think I said it and didn't write it. Okay. Probability of juniors in art. So total number of juniors in art club was 16. That's the 16 right here. Okay. Total art club members. Probability was 58 over 115. The total art club numbers is 58. Okay, same answer both ways, yes? So rather than totally thinking about the probability, the denominator is going to be the same, so we can just look at numerators. Okay. Questions on that one? Okay. Now, and the others on another page, I still have the chart available here. We have some questions asked just to kind of get the feel for this conditional probability. Was the probability that a member of the drama club is a sophomore? So what's the probability that a member is, probability that the student is a sophomore given they're a member of drama club? Okay, in words, what am I putting on top? What? Okay, number of sophomores in drama club, right? So officially in words, it's the probability that they are a sophomore. What am I doing? Sophomore? I don't know what I'm trying to spell here. Sophomore and a member of drama club divided by the probability of what? Not sophomore, but drama club. So it's probably both on top, probably of the second one on bottom. So probably they are a member of drama club on bottom. Okay, now I say probability because that's officially what we're supposed to be doing. You can shortcut the denominators out, okay? As Patrick mentioned, probability of sophomore in drama. What do we have there? That was 3. Officially, it's 3 out of 115. Okay? Probably a student is a member of drama club. What is that? 17. And officially, I can say it's 17 out of 115. But again, those 115s, when we divide those fractions, would cancel. Does 3 17ths reduce?
No.
Well, no, I just boxed it. I just made it obvious, didn't I? Okay? Or the fact that they're both prime and they're not going to reduce. Okay. Learn the setup here, folks. It's probability. This right here is not difficult probability, but you have to know the setup. Otherwise, it does become difficult. Now, the second one. What is the probability that a sophomore is a member of the drama club? Or the probability of drama given that they are sophomore? Now, is this a different question?
Yes.
Yes. It's hard to tell, but if you look, probably a member of the drama club is a sophomore. Okay, that is probably they're a sophomore, but they have to be a member of the drama club. This one was probably a sophomore is a member of the drama club. Well, this is what's probably they're in drama given they are a sophomore. Okay, so learn to read it and turn it into that. What are we doing on top? The probability of what? Probability of both. So probability of drama, being in drama and a sophomore. How many is that? 3. What's going on bottom this time? Probability they are a sophomore. And how many sophomores do we have? Ah, there it is, 36, thank you. Okay, what do your brains know about 3 out of 36? Can reduce, yes? Reduces to 1/12. Okay. Okay. Now, follow-up question. Is the probability of sophomore, a student being a sophomore given they are a member of the drama club, the same as the probability of a student being in drama club given they are a sophomore? Okay, I've already talked about this a little bit, but are they the same? Definitely not, right? We just did both of them. We got 2 different answers. Okay. And what's going on here? The first one was comparing the 3 students, how many the students in sophomore, they're sophomores and in drama club, to how many students are in drama club. The second one compares it to how many students are sophomores, right? Okay, so both cases it's the 3, but it's what it compares it to. Okay. How do I want to explain this? Obviously, the answer is no. Okay. Let's see, probability of soft drama, and I'm going to say officially, compares sophomores in drama club to all drama club members. Okay. While the probability of student being in drama, given they are a sophomore, compares, again, it's sophomores in drama, so that's the same. But this time it's going to compare it to all sophomores. Okay. So, get some kind of explanation down. Understand the difference there. If you don't have a calculator by your side, you're probably going to want a calculator by your side because some of these, like the next one, for instance, we're going to end up going to a decimal or a percent. Okay. Start reading the next one when you're ready. Okay. Diego wonders whether the amount of sleep he gets is related to the amount of coffee he drinks. For about 10 weeks, he records how many cups of coffee he drinks each morning and how many hours he sleeps that night, rounded to the nearest hour. Based on this data, what is the probability of 8 hours given 0 cups? And then it's asking us to round our answer to the nearest whole percent. So expressing it as a percent. Okay. What is this probability asking us to find? What are we putting on top there? Probability of what? Okay, so probability of 8 hours and 0 cups over what's going to go on bottom? The probability of 0 cups. Okay. What do you got for the top? Probability of 8 hours and 0 cups. So 8 hours of sleep given 0 cups of coffee. Okay. 12 right there. Officially, the probability would be 12 out of the 72 altogether. But what about the probability of drinking 0 cups of coffee? There's 22, and officially it would be out of 72. But again, if they're both out of 72, that's how I can shortcut it. What do you know about 12 out of 22? I guess they don't want a fraction, do they? My brain says 6/11. What's that become as a decimal? Wait, 0, 5, 4, 5, 4, so on and so forth. What's that become as a percent? (54.54%). In this particular problem, we want to say 55% if it's rounded to the nearest whole percent. Okay. Again, it's probability, isn't it? Okay. At the top of the next page, it talks about conditional probability and independent events. So the idea of how we can use conditional probability to test if 2 events are independent or not independent. So let A and B be events. where the probability of A cannot equal 0 and the probability of B cannot equal 0. So just events to make this work. If events A and B are independent, then the conditional probability of B given A equals the probability of B, and the conditional probability of A given B equals the probability of A. Okay, so easier to look at it in symbols, okay? So this would be the test if they are independent. Probability of B given A is going to equal the first part. It's going to be the same as the probability of B. Probability of A given B is going to be the same as probability of A. Okay? And then this is just the, I believe converse is the word I want here, where it's just stated backwards. It's the same thing. It's just saying if the conditional probability is true, then the events are independent. Okay, so as opposed to saying if the events are independent, the conditional probabilities are true. So you have the same piece of information. Okay, so the idea is that we can test these and we can know if events are independent, if there's any question about it. Okay, so we're going to look at an example here. And it asks us to use the test for independence. The table below shows the vehicles in a parking garage one afternoon. A vehicle in the garage will be selected at random. Let B represent the vehicle as black, and V represent the vehicle as a van. Are the events B and V independent or dependent? Okay. So what are we testing here? We want to know if they're independent or dependent. If you go back up to the statement above, probability of B given A has to equal probability of B, probability of A given B has to equal probability of B. So what are we going to have to start off finding? We're going to have to find our conditional probabilities, yes? Okay. On this particular problem, they use B and V. So I'm going to start off saying let's find the probability of B given V. Okay. So I'm doing the probability of B given V. On top is going to be what? Probability of black and a van. So B and V divided by probability of what goes on bottom? Van. So V. Okay. How many options do we have for black and van? Okay, 3. Out of how many options for probability it's a van? Also 3, yes? And 3 over 3 equals 1. Now, what do we have to test to see if this is independent or not? Go back up to the top, right? If it's probability of B given A, it needs to equal probability of B. So this is probability of B given V, so it needs to equal probability of B. What is the probability of just B? B being what in this case? Black. So what's the probability that the vehicle is black? 13 out of 22. What do we know right here? Are those probabilities the same? They're not, are they? So what I know right now is that the probability of vehicle being picked given it a black vehicle being picked given it's a van does not equal the probability of a black vehicle. Now, we're going to go ahead and test the other way too, but what does this support right now? These events are, okay, not independent, thus, yes, dependent, okay. Now, officially, could we get away with stopping here possibly? I would say probably because they have to both work for it to be true. But in all honesty, the probability they're going to both work or both not work. Okay? So let's reverse this though real quick. Probability the vehicle is a van given it's black. So V/B. On top is the same, right? B and V divided by, so probability the vehicle is black in a van divided by the probability it is black. Okay, black in vans, we already had what? 3. Probability a vehicle is black. How many black vehicles do we have?
13.
13. Now, to test for independence. What are we testing to see if this is equal to? We're testing your initial part, not the condition. So probability that the vehicle is a van. How many vans? 3 out of? 3 vans out of how many total vehicles? 22. What are we showing here? Probability of a vehicle given it's black. Or I keep saying vehicle for V. A van given that it's black does not equal the probability that it is a van. Okay, so together, what did I just show? These events are dependent, right? They are not independent. So between both of these, that is our proof that events B and V are dependent.
But isn't it a 100% chance that if it's a van, black?
Yes.
So how would black vans not equal to the amount of vans?
Okay, say that again.
How would the total number of vans not equal the total number of black vans?
Because the total number of vans is the total out of all the vehicles.
I thought you were just as much as vans.
Depends on which part you're looking at here. Which part were you looking at?
The P V is not equal to P of V.
Right here.
Yeah.
Okay. So this is the probability the vehicle is a van given it's black.
Which should be 100%. If it's a van, it's going to be.
No, this way, okay, this way is 100%. This way is not. Because probability that it's a van given it's black, there are more black vehicles.
Oh, I see what you're talking
I thought you were talking about up here. There it's 100% chance, but we reversed it.
about. I get what you're saying now.
Okay. So I know it takes my brain a moment to wrap itself around all of this. So I totally expect the same for you guys. It's going to take a moment to wrap your brain around the conditional probability. That's why we practice, right?
I don't know who's selecting vehicles at random in a parking garage, but that's not like their issue.
You know, we all know that when it comes to math problems,
Like,
you get some really weird ones. You get some really weird ones because you think, in reality, who does this? You know. Okay. One more using this same chart. Let R represent the vehicle as red, so R is defined to be red, and C represent the vehicle is a car. Are the events R and C independent or dependent, and explain? So again, we're using our test, right? So again, it's a matter of practicing how we set it up. What do you want to set up first? Okay. Probability of R/C, which is probability the vehicle is red, given it is a car. On top, it's probability of red and a car divided by probability that it is a what? A car. The condition there. Okay. Red and car. How many red cars do we have? 5. Probably it's a car. And technically that would be 5 out of 22, right? Probably it's a car. 11. Technically 11 out of 22, but we're shortcutting that. So 5 11s. Now, what do we have to compare this to? Probability of the first main piece, not the condition. So probability of R. What is probability a vehicle is red? 7 out of 22? Glad you guys can keep me straight on some of this. Okay, what did we just show there? Okay. Probability of red, given it's a car, does not equal the probability of red. Okay. Reverse it, just to double check ourselves. So the other way is the probability of a car given it's red. On top, I hope you realize we're just always doing both, right? So probability of car in red divided by probability of, what was my condition? And that is red. Okay. Probability that it's a car and red. And that again is 5 red cars. Divided by probability it is a red vehicle. How many red vehicles do we have? 7. Okay. And we're going to compare that to the main probability there, right? Not the condition, the main probability. So probability it is a car. Probability it's a car. What do we got? 11 out of 22. We want to be fancy. What do we know about 11 out of 22? It's 1/2. Okay. Ultimately, though, what did we just figure out? Probability of it being a car given it's red does not equal the probability of a car. So, what do we know about events R and C? Okay, events R and C are dependent again. Okay, it failed the test for independence. Okay. Starting to? Okay. There's part of me that said, call it quits, but I think this last example will pull these together. So one more, then we'll call it quits for the day. Now we're talking about girls and boys taking French or not taking French. Okay? So the table shows data for the junior class at a high school. Obviously not our high school. A student from the junior class is selected at random. Let G be the event the student is a girl, and F be the event the student is taking French. Are events G and F independent or dependent? Okay. Short of just looking at this and explaining, what's our official test? Yeah, let's test our probabilities here. So probability, if we start with G/F, probability the student is a girl, given that they are taking French. So on top, it's going to be, you know what goes on top? Probability of both, right? A girl and taking French, divided by the probability of what? The condition, the French. So, what do we have here? Okay. 45 that are girls and taking French, divided by, how many are taking French? 75. Not what you said?
No, I said 300 because I love the house to sit down.
Fair enough. I think that's one of the hardest things is getting the right number off the chart.
Yeah.
45 out of 75. I know that reduces. I see fives. Actually, it goes bigger. Yeah. Yeah. It technically reduces by 15 if you catches it. If you catches it. Or my brain went to divide by 5 and then done, gosh, I can't talk, divide by 3. One way or another, you get to 3/5. What are we going to compare that to? Probability the student is a girl. So we're comparing the conditional probability to just the regular probability. What is the probability the student is a girl? Now, just a girl. How many girls are there?
300.
Out of? 500. Oh, what do we know about 300 out of 500? 3 out of 5. What do we know right now? Probability the student is a girl, given they are taking French, equals probability the student is a girl. Now, can we stop right here? You definitely cannot in this case. Okay? If this is truly going to work, both ways have to work. So, probability, it is a student taking French, given they are a girl. So reverse it. On top, we're going to put both French and girl, divided by the probability of the condition, which is girl. Well, the student being in French and a girl is the same as the student being a girl and in French, and we already know that number to be 45. Probably the student is a girl. How many girls are we looking at? 300. Well, I think they both divide by 15 again, don't they?
Yeah, 300.
Or if all else fails, they divide by 5, and then you'll figure out they divide by 3 again, so 3/20. Now, what am I comparing that to? The conditional probability compared to just the regular probability. And again, you get confused and forget what you're comparing it to. Go back to the rule, right? That's why we have our notes right now. It's day 1. You don't have to have this memorized or, be perfect at it yet. Probability the student is taking French. 75 out of 500. Well, I know they both divide by 25. That's 3 and that's 20. Surprise, surprise. We just figured out the probability of a French student, probability of a student being a French student given they are a girl, equals probability the student is in French. Okay, guys. What do we know? Okay, these passed our test. The events are independent. Okay, right at the bell. Tomorrow, we will finish these notes, and Savas 12.2 will become available. I don't have it out there right now. I know I don't, but I may get it out there later today. What's important to get finished today? 12.1. Get it done, guys. Okay?
Oh, you're right.